morning, everyone. Welcome back to the Deep Dive. We're here to cut through the noise and really get into the details of complex tech topics. And today, we're looking at something absolutely fundamental to every single computer, the motherboard. You know, we talk about the CPU as the brain, and we recently did a whole deep dive on memory, from registers right down to persistent storage. Remember that one? But how do all these amazing parts, the processor, the RAM, your graphics card, even your keyboard and mouse, how do they actually connect and work together? How does it stop being just a pile of parts? That's where today's unsung hero comes in. The motherboard. It's like the central nervous system and the skeleton all rolled into one. It's the main communication hub, the thing that ties everything together. Honestly, understanding the motherboard is key if you're building a PC, thinking about upgrades, or just want to know what makes your machine tick. And joining me to help navigate this pretty intricate landscape is our expert. Really glad you could be here.
Hello, everyone. Thank you for having me. It's a great pleasure to be here to discuss this important topic.
Fantastic. So, for this deep dive, we're going to tackle the motherboard piece by piece, Q&A style. We'll kick off with the physical stuff, the anatomy, the different sizes. Then we'll dive into the chipset, the board's traffic controller. After that, we'll look at the data highways, the system buses, and wrap up with the firmware, the crucial bit that first wakes the system up. By the end, you'll really see how the motherboard defines your whole computer's potential. Ready to jump in?
Absolutely. Let's get started.
Okay, let's start with the basics. The motherboard itself, it's this complex printed circuit board, right? A PCB, with all these little copper lines, the traces connecting everything. So when you first look at one, what are the really obvious features? The ones for plugging in the main components, like the CPU and RAM.
All right, when you hold a motherboard, a couple of things really dominate the landscape. The most prominent is usually the CPU socket. That's where the processor, the brain, physically connects. And the type of socket is crucial. You've got things like Intel's LGA land grid array, like LGA 1700, where the pins are on the socket itself. Or historically, AMD used PGA pin grid array with the pins on the CPU. Which socket you have dictates exactly which CPUs you can even install. It's a fundamental choice.
Locks you in right from the start, basically.
Exactly. And right near that, you can't miss the RAM slots, or DIMM slots, as they're properly called. These long slots are for your system memory modules. Most boards you buy for a desktop will have 2 or maybe 4 of these dual inline memory module slots. And just like the CPU socket, the type of slot matters. It tells you if you need DDR4 RAM or the newer, faster DDR5. So yeah, those two areas, CPU socket and RAM slots, tell you a huge amount straight away.
It's amazing how much those define. Okay, but it's not just CPU and RAM, right? Motherboards let you add more stuff. What about expansion slots and storage connectors?
Good point. Beyond those core components, the motherboard is all about expandability. That's where expansion slots come in. Nowadays, these are almost entirely PCI Express or PCIe slots. You'll see different lengths, the long by 16 ones, shorter by 8, by 4, even tiny by 1 slots. That big by 16 slot. Wow. That's usually for your graphics card. Super important for gaming or heavy visual work. The smaller ones might take, say, a Wi-Fi card, a sound card, or maybe even extra high-speed storage.
High-speed storage. That brings us to the connectors.
Yep. You'll still find the traditional SATA ports. Those are for your regular hard drives or older style SSDs. They work fine, but the real speed demons now use the M.2 slots. These let you plug NVMe SSDs, these little gum stick-shaped drives, directly onto the motherboard. The speed difference compared to SATA is just enormous. It's a huge upgrade for system responsiveness.
It's like night and day sometimes, yeah.
Totally. And of course, you've got the essential power connectors. There's the big 24-pin one for the main board power, and usually a smaller 4-pin or 8-pin connector just for the CPU. Needs its own juice. Oh, and don't forget the rear I.O. panel. That block of ports on the back, USB, Ethernet for your network, audio jacks, video outputs like HDMI or DisplayPort. That's your connection to everything external.
Great overview of the parts. Now, you mentioned fitting things together. Motherboards come in standard sizes, don't they, to make sure they fit in cases. Could you break down the common ones, like ATX, Micro ATX, and Mini ITX?
Absolutely. These standardized sizes or form factors are super important. They ensure that a motherboard from, say, Asus will fit in a case from Cooler Master and work with a standard power supply. It avoids chaos.
Thank goodness for standards.
Right. So the big one, the longtime standard for desktops, is ATX Advanced Technology Extended. ATX boards are full-sized. They offer the most physical space, usually meaning 4 RAM slots, and the most PCIe slots for adding lots of cards. Ideal for, serious gaming rigs or workstations where you need maximum flexibility.
Got it. The big powerhouse option.
Then you have Micro ATX. It's basically shorter than ATX, but the same width.
Yeah.
Because it's shorter, you get fewer PCIe slots, but it's a really good middle ground. Offers a great balance of features and size, often a bit cheaper too. Very popular for mainstream builds.
Okay, a good all-rounder.
And finally, there's Mini ITX. These are tiny, designed specifically for compact, small form factor or SFF builds. Now, the trade-off is limitations. Usually only 2 RAM slots and just 1 PCIe by 16 slot, enough for a graphics card, but that's about it for expansion. But don't underestimate them. You can build incredibly powerful portable gaming PCs or sleek home theater PCs with Mini ITX. It's all about prioritizing size. So ATX for max features, micro ATX for balance, Mini ITX for compactness.
Okay, that covers the physical layout really well,
Mhm.
but something has to manage all the communication on the board, right? Like a traffic controller. That's the chipset, isn't it?
Exactly. The chipset is the intelligence hub managing data flow.
And historically, I remember reading it used to be 2 separate chips, the Northbridge and Southbridge. What did they each do?
That's right. For a long time, we had a 2-chip system. The Northbridge was the high-speed controller. It was usually physically located north, closer to the CPU. Its main job was handling the really fast connections, the link between the CPU, the main memory RAM, and the primary graphics slot, whether that was the older AGP or early PCIe. Think of it as managing the express lanes.
CPU, RAM, graphics, the fast stuff.
Precisely. Then you had the Southbridge. This one handled all the slower input-output, or I/O, functions. It connected to the Northbridge, and it managed things like your hard drives and SSDs through SATA ports, your USB ports for peripherals, the onboard audio network controllers, and any older, slower PCI slots. All the general housekeeping I/O, basically.
Okay, Northbridge for speed, Southbridge for everything else. But that changed, right? Why did we move away from that?
It did change, yeah. The 2-chip design started to become a bottleneck, actually, especially the link between the Northbridge and Southbridge.
Ah, okay, so how did it evolve? What do we have now with this platform controller hub or PCH thing?
Well, the big shifts came when CPU manufacturers, both Intel and AMD, started integrating more functions directly onto the CPU itself. Modern CPUs are much more like systems on a chip or sockets. They now typically include the memory controller right on the CPU die. This means the CPU talks directly to the RAM, which is way more efficient, super low latency.
Direct line to memory. Makes sense.
And they also integrated a primary PCI Express controller onto the CPU too. This gives a direct high-speed link to the main graphics card slot, and often to 1 or 2 of the fastest M.2 slots for NVMe SSDs, again, cutting out the middleman for speed.
So the CPU took over the Northbridge's main jobs.
Essentially, yes. With those critical high-speed functions moved onto the CPU, the traditional Northbridge wasn't really needed anymore. So the modern chipset is now typically a single chip. Intel calls it the Platform Controller Hub, PCH. AMD has a similar concept. It's basically an expanded, more powerful version of the old Southbridge. It connects to the CPU via its own high-speed link, like Intel's DMI or an AMD equivalent, using PCIe lanes, and it manages all the rest of the system's I/O. That includes additional PCIe lanes from the chipset itself, all the setup ports, most of the USB ports, onboard networking, audio controllers, everything else, really.
And the specific chipset model, like a Z790 versus B760, determines what extra features you get.
Exactly. The PCH model dictates the number of available USB ports, SATA ports, the number and speed of the extra PCIe lanes it provides, and sometimes enables advanced features like CPU overclocking. So the chipset choice still really defines the board's overall feature set, even as a single chip.
That evolution makes a lot of sense for performance. Okay, so we have the components in the controller. But how does the data actually move between them? You mentioned buses, like data highways.
Precisely. Data doesn't just magically appear where it's needed. It travels along specific pathways called buses. A bus is essentially a communication system, a shared pathway for transferring data.
And the main system bus, the one connecting the core parts, has different components itself, right?
That's correct. Logically, we can think of the system bus as having 3 main parts that work together. First, there's the data bus. This is, well, for the data itself. It's the path the actual information travels on between the CPU, memory, and other devices. The width of the data bus, measured in bits like 64-bit, determines how much data can be moved at once. Think of it like highway lanes. More lanes mean more traffic capacity or higher throughput.
More data per cycle. Got it. What else?
Second, the address bus. When the CPU needs to read or write data from a specific spot in RAM, it needs to specify where. The address bus carries that unique memory location address. It's like the postal address for data.
Telling the system where to look. Okay. And the third?
The third is the control bus. This carries command signals from the CPU's control unit instructions like read from memory or write to device. It also carries timing signals from the system clock to keep everything synchronized and status signals back from devices. It basically orchestrates the whole data transfer process, making sure everything happens in an orderly fashion.
Data, address control, working together. You mentioned the address bus tells the system where to find data in memory. Its width seems really important, especially thinking back to the limits of older systems. Can you elaborate on that jump from 32-bit to 64-bit computing?
Oh, absolutely. The width of the address bus is directly tied to the maximum amount of physical memory a CPU can access. There's a fundamental limit. A 32-bit address bus can generate 2 to the power of 32 unique addresses. That works out mathematically to 4,294,967,296 bytes, which is exactly 4 gigabytes, or 4 gigabytes.
Ah, so that's why 32-bit Windows could only use 4 GB of RAM. It wasn't just software.
Exactly. There's a hardware limitation imposed by the address bus width.
Yeah.
No matter how much RAM you physically installed, a 32-bit system simply couldn't see or address more than 4 GB.
Wow. Okay, so the move to 64-bit.
Was revolutionary. A 64-bit address bus can theoretically address 2 to the power of 64 bytes. That number is astronomically large, 16 exabytes. Far, far more memory than we can currently even dream of installing in a machine. But the key thing is, it completely smashed that 4 GB barrier. It allowed systems to effectively use huge amounts of RAM, 16 GB, 32 GB, 64 GB, 128 GB, and more, which is essential for today's demanding applications, games, virtual machines. Everything really is a monumental shift.
Definitely feels like it unlocked modern computing in many ways. Okay, shifting from those internal buses to how we add extra stuff, the expansion slots. You mentioned PCIe is dominant now. How does it actually work compared to older standards?
Right, PCI Express, PCIe, has been the standard for, gosh, nearly 2 decades now. It's very different from the old PCI bus it replaced. PCI was a parallel bus, and importantly, it was shared. All devices on the bus had to share the available bandwidth. PCIe, on the other hand, is a serial point-to-point connection. Think of it like each device gets its own private high-speed lane directly to the chipset or CPU, depending on the slot. No sharing, no contention.
Point to point, like a dedicated connection.
Exactly. And the way it achieves scalability is through lanes. A PCIe connection is made up of one or more of these serial data links or lanes. You can have a connection that's by one lane, by four lanes, by 8, or by 16. More lanes equals more bandwidth, directly proportional. So that big graphics card slot is usually by 16 for maximum data throughput, while a Wi-Fi card might only need my 1 slot. It's very efficient at allocating bandwidth.
And this standard keeps getting faster, right? We hear about PCIe 3.0, 4.0, 5.0.
Constantly evolving. That's one of its strengths. We've gone through PCIe 1.0, 2.0, 3.0, 4.0, 5.0, and 6.0 is already defined and starting to appear. The key takeaway is that each new generation roughly doubles the bandwidth per lane compared to the previous one. So PCIe 4.0 is twice as fast per lane as 3.0, and 5.0 is twice as fast again.
Wow, doubling each time.
Pretty much, yeah. And this relentless speed increase is absolutely vital. Think about modern graphics cards processing huge amounts of data for high-resolution gaming or AI tasks, or those incredibly fast NVMe SSDs we talked about. They need that bandwidth. PCIe keeps evolving to make sure the connection isn't the bottleneck.
Makes sense. You need faster highways for faster cars. And while we're on connections, we can't ignore USB, can we? It's everywhere for external stuff. How has that evolved?
Oh, definitely. Universal Serial Bus, USB, is another cornerstone of motherboard connectivity. Its strength is its versatility, ease of use, hot swappable, plug and play, and it can even provide power. Its evolution is also about speed. We started with the very slow USB 1.1 at maybe 12 megabits per second. Then USB 2.0 was a big jump to 480 Mbps, which was standard for ages. Then came the USB 3.x series, pushing speeds into the gigabits per second, 5 Gbps, 10 Gbps, even 20 Gbps, depending on the specific version. And now, the latest iterations like USB 4 and its close cousin Thunderbolt, which often uses the same USB-C connector, are incredible. They integrate other protocols like PCIe and DisplayPort right into the USB connection. This gives them massive bandwidth, typically 40 Gbps or even more, enough to drive multiple high-resolution monitors, connect external GPUs, or run super-fast external storage, all through one single cable. It's really amazing how versatile that one port has become.
It really is incredible how much connects through the motherboard.
Okay, let's shift focus to the very beginning of the process. When you press the power button, what actually happens first? How does the computer even start? That's firmware, right?
That's exactly right. When you apply power, the CPU itself is initially, well, dumb. It doesn't know what to do. It needs a set of initial instructions to kick things off. That initial software is called firmware. It's stored on a special chip, non-volatile memory, right on the motherboard itself. It doesn't get wiped when you power off. It's the first code that runs.
Okay, the very first step. And for decades, that firmware was the BIOS, wasn't it? What did the BIOS actually do, and what were its problems? Yes, for over 30 years, the BIOS basic input-output system was the standard. Its job upon power-on was crucial. First, it performed the POS test, the power-on self-test, basically checking. Is the CPU okay? Is RAM detected? Is there a graphics card? Just the essential hardware checks. If the post-it passed, the BIOS would then look at your storage drives, searching for something called a master boot record, or MBR. The MBR contains information on where to find the operating system's bootloader. The BIOS would load that bootloader into memory and then hand over control, letting the operating system take over the rest of the startup process.
Sounds straightforward enough. What were the limitations then?
Well, the BIOS had some pretty significant drawbacks due to its age. It was based on a 16-bit architecture, which limited its capabilities. The interface was usually just basic text on blue screen, navigated with arrow keys, not very user-friendly. But the biggest technical problem, the one that really forced a change, was its inability to boot from storage drives larger than 2.2 terabytes. As hard drives and SSDs got bigger and bigger, this became a major roadblock.
Ah, that 2.2 TB limit. I remember that being a big deal. So BIOS couldn't handle modern large drives. What replaced it? That's UEFI.
Exactly. The successor is UEFI, which stands for Unified Extensible Firmware Interface. It was designed from the ground up to overcome all those BIOS limitations. Its advantages are huge. Firstly, it fully supports booting from much larger drives. We're talking drives many, many terabytes in size because it uses a modern partitioning scheme called UEID partition table, or GPCI, instead of the old MBR.
So goodbye 2.2 TB limit. What else?
UEFI typically offers a much nicer graphical user interface, often with mouse support, making it way easier to configure system settings. You get icons, menus, it looks like a modern program. Plus, its architecture allows for potentially much faster boot times. It can initialize hardware more efficiently and in parallel sometimes, getting you to your operating system quicker. It's just a far more modern and flexible foundation.
Faster boots are always good. Now, you mentioned flexibility, but UEFI also brought some major security improvements, didn't it? What was the key one?
Yes, this is arguably one of the most important contributions of UEFI. Secure boot.
Secure boot. Heard of it. How does it work?
It's designed specifically to combat a nasty type of malware called bootkits or rootkits, which try to infect your system before the operating system even loads, making them really hard to detect and remove. Secure boot works by creating a chain of trust. It ensures that the firmware itself, the operating system bootloader, and sometimes even drivers, are all digitally signed by a trusted authority, like the motherboard maker or Microsoft. Before UEFI loads the next piece of software in the boot process, it checks its digital signature. If the signature is missing, invalid, or tampered with, UEFI simply refuses to load it and stops the boot process.
So it stops malware hijacking the boot sequence right at the start.
Precisely. It prevents unauthorized code from running before your main operating system security features have even had a chance to load. It's a really fundamental layer of protection for modern PCs.
That's a critical feature indeed. Okay, we've covered the anatomy, the chipset controller, the data buses, the expansion slots, and the firmware. Bringing it all together now. How would you summarize the motherboard's role in uniting everything?
Well, when you step back and look at all those pieces, you see the motherboard isn't just a passive board. It's really the active, sophisticated foundation that ties every single component together into a working computer. Its form factor sets the physical boundaries and potential of the build. Its chipset acts as that crucial traffic director, managing the complex data flow. That data flows across the system buses, those vital highways connecting the CPU, memory, and everything else. The board's expansion slots like PCIe and its vast array of interconnects like USB define its ability to grow and connect to the outside world. And finally, the UEFI firmware provides that initial spark, performing the essential checks and securely launching the operating system. It truly orchestrates the entire process from power on.
So it really is the heart of it all. The choices made in the motherboard, its quality, its features, the chipset it uses, they really dictate the overall performance, the stability, and even the future upgrade potential of the entire system you build on it.
Absolutely. It underpins everything. Choosing the right motherboard for your needs is one of the most critical decisions when building or upgrading a PC. #outro.
What a fantastic deep dive. We've really unpacked the motherboard today, haven't we? From its physical layout, the sockets, the slots, the connectors, and how form factors like ATX, micro ATX, and mini ITX influence your build.
to the evolution of the chipset, moving from that old Northbridge, Southbridge design to the modern integrated PCH acting as the central I/O hub.
Right. And we explored those data highways, the data address and control buses, and saw why that jump to 64-bit addressing was so important. Plus, the dominance of PCIe for expansion and USB for peripherals.
And finally, understanding the crucial role of firmware, the move from legacy BIOS to the much more capable and secure UEFI, especially with features like Secure Boot protecting the startup process.
It just goes to show the motherboard might not always get the spotlight like a CPU or GPU, but it is absolutely essential. Understanding it gives you, the user, so much more insight into how your computer works and how to get the most out of it. We hope this helps you appreciate this core component a bit more. Now, join us next time as we continue our journey through computer hardware. We'll be exploring interfacing with the machine, input-output, I/O systems, basically how we actually interact with our computers. Thank you so much for joining us today for this deep dive into the motherboard. If you found this discussion valuable, please do consider subscribing to our channel, Tech AI and Beyond, for more in-depth explorations of the technologies shaping our world.
Thanks, everyone.
We'll see you next time.